2, 1. Alright. Welcome to the penultimate video, our second to last one. Okay. So, we've been hanging out with Riemann integration, and we have, first of all, rigorously defined it in terms of epsilons and deltas. We have dissected the various properties it has, and we have, of course, now demonstrated the fundamental theorem of calculus. So, what's left? Well, a lot more, to be honest. Just right, the analysis story does not end with the fundamental theorem of calculus. If anything, it begins with the fundamental theorem of calculus. So where do you go next? So let's talk about a very powerful technique that the fundamental theorem of calculus helps out with, and that is integral defined functions. So there are a lot of functions out there that show up in various applications and just other mathematics that are defined via integration, and perhaps the most famous one is our good friend the natural log. So we define, right, because we have not rigorously constructed the natural log, we have not explained at all what this function even is, right, based off of just the axioms of the real numbers. Of course, we know log exists from our everyday math experience, but we haven't constructed it, using the least separate bound property, which you can do. But we're not going to go that way because we have the Riemann integral at our disposal. And indeed, the function 1 over t is nice and continuous on this domain, which means I have access to this integral. And as we have already proven a whole bunch of stuff, I know a lot about functions that look like this, in addition to knowing that they're continuous, they're also differentiable, and a bunch of other fun stuff. Now, of course, following up on that, we can kind of see this should coincide with our usual intuition of what the natural log is, because its derivative is 1 over x. I already know that, so using that to create it, not a bad idea. Okay, so in particular, as we proved last time, this is indeed the unique differentiable function with the following conditions. At 1 it's equal to 0, and its derivative is 1 over x. That's good for all positive x. So, well, there we go. Beautiful. All right, so moving on, now that we've recapped what we remembered, any continuous function, there is a unique differentiable function satisfying whatever the initial condition is. We're going to choose log of 1 to equal 0, and satisfying this derivative condition. All right. Okay, so notationally speaking, when it comes to log, there are two notations that are used. For the natural log, you are probably pretty familiar with ln of x, log d natural. However, IMN level, in fact, uses this in the textbook. We're adults now. Let's use log of x. We all know what we need. This is the natural one. This is the one to use. It should be the one where we don't specify the base. Log base 10 if you need it, or log base 2, you would indicate it. So I'm just going to use log for this. This is kind of standard with an analysis. When you get to a certain point, people just give up on ln of x. Just go, it's fucking log. So I'm going to use log. That being said, be aware on your homework, the homework problems on ln, on natural log, will use ln. Okay. Anyway, so, hey, we already know by construction that I have a nice, continuous, and differentiable function now. What are some other properties that log has? Okay. Oh, and by the way, use this. Forgot I had that there. All right. So what are some other properties log has? And probably the most famous one is that the log of the product is the sum of the logs. So log allows us to transform multiplication into addition, and vice versa. Log lets us turn sums into products. So before we prove this, it's worth noting that this gives you the pretty standard way of creating infinite products of things, because we can create infinite sums, and log lets us turn sums into products. So there's a way of getting the theory of infinite products out of this. Okay. Anyway, so how do you prove this? Well, we're gonna be a little sneaky with this one, right? Because at first glance, it seems like this might be pretty difficult to prove via integration, right? If I write out the integrals here, it's not immediately obvious why this would be true. But we're going to be sneaky, because even though there are two things flying around here, we really only need to worry about one. And so what we're going to do is create a function, where you know x is fixed, and so is y. So let's create a function using one of our x's. Specifically, let's create the function log of xt minus log of x. So in this case, y is something we can plug in. So if I were to prove, oh, I don't know, that this function here sends, 1 to 0 and its derivative is 1 over x, well then this has to equal log of t, and then you just plug in y. Oh, isn't that convenient? Indeed, if you plug 1 into this, you get 0, and if you take its derivative, now note this derivative is with respect to t, x is a fixed input, fixed real number. So by chain rule, we know the derivative of this is 1 over the inside, multiplied by the derivative of the inside, which would just be x. This is a constant in the eyes of this derivative, so it's gone. And hey, the derivative is 1 over t. So it's got to be that f of t is equal log of t, and that's good for all t. And plug in y, and we're done. Beautiful. We've proven log's very famous property that it turns products into sums. And also takes sums and turns them into products. Into log of a product, maybe I should be a lookout for that. Okay, there you go. All right, so this is a neat little trick. Because I feel like Leibniz actually do this proof. Leibniz is like a more direct, like actually work with the integrals, which this is so much easier. The integral argument isn't bad, and it's kind of neat to see, but you kind of ultimately end up making this sort of argument, so it's anyway. Alright, beautiful. So now that we're equipped with this property of log, there are a bunch of things about log we can quickly establish. So the first one is that a very famous property of logs, log of x to a power, is n log of x. Alright, so let's verify that. So since we're dealing, of course, with natural numbers, we will, of course, use induction, plug in 1, there you go, it's cheaply for free. Now suppose it holds for some m. Well, if we look at log of x to the m plus 1, well, it's log of x to the m times x. Log takes products and turns them into sums of logs. And by hypothesis, we know we can pull the m out, and then, hey, add it together, get what you want. Beautiful. Nice and easy inductive argument. Yay! So, not too much to unpack there. Just basic induction argument, use what we already know. Good stuff. Okay. Now, somewhere in your brain you might be going, oh, I remember if there's like another power here, and then you can always pull that out. Maybe we'll see that, I don't know. Alright, so for natural numbers it's certainly true. For other ones, hold your horses on that. Okay, so another property of log that's beyond important is that log takes 1 over x and spits out negative log. Now note, 1 over x is x to the negative 1, so it's basically the previous result, but now instead of restricting our attention to natural numbers, now we can talk about, well, what happens when I, try other exponents. Alright, so the way to pull this one off is by recognizing two things about log. First of all, log of 1 is 0, and then log of a product is the sum of the logs. Okay, and that's it. The end. Super easy, right? These are rapid fire. This is just boom, boom, boom. Get all these cool properties of log. All right, good stuff. So, all right, we are now equipped with. Sorry if you're hearing noises. Equipped with some basic properties of logs. What are some other things we can do? Here's one that you may not immediately remember or have at the ready, but it's a very powerful and important fact about logarithms. So here is an inequality involving logs, and this inequality is, ooh, is this a good one? There is a lot of neat math you can pull off with just this inequality, as you may or may not see in your homework. I don't know. All right. Yeah, and so when it comes to log and our thoughts of calculus, we don't really think of inequalities, well, because we don't really work too much with inequalities when we're actually in calculus. It's really more of the analysis side of things. But yeah, so log is always less than or equal to x minus 1, and log is always bigger than 1 minus 1 over x. Now the 1 minus 1 over x one is not that impressive as x gets really big. but it's got its uses. And the same thing on the right-hand side. Once x is very large, it's, as we just saw, logs take exponents and pull them out. So log of 10 to the 3 million is 3 million times log of 10, and log of 10 ain't that big. So yeah, obviously 10 to the 3 million is going to beat it. All right. So, how do you prove this? Well, remember our definition of log. Our definition of log was based via integration. Okay, so there's actually three cases to consider because we want to apply some results of integration. So first of all, if x is bigger than 1, well, then for every t that lives between 1 and x, well, then we know 1 over x is less than or equal to 1 over t, which is less than or equal to 1, which means the integral that defines log is bounded above by the size of the interval times the upper bound, and bounded below by the size of the interval times the lower bound. And since this is a log right here, and we got multiplied the 1 over x out, we get the inequality we want. When x is equal to 1, we obviously just get equality, because on both sides we have 0, and log of 1 is 0. So nothing too spicy there. The only thing to consider now is when x is actually less than 1, and then here we're going to use our integral trick of when the interval is going backwards, we negate. So note, just like before, this has to hold, but now we're going to throw a minus sign across the board, and the minus sign here will flip the order of integration, give us our definition of log, and there we go. Holds everywhere. Beautiful. All right, so like I said, that definition of that inequality here with log may not be something that you immediately have at the ready, but it is an incredibly powerful tool, and we'll see it in effect later on in the slides today, and maybe I'll see it in your homework, I don't know. Okay, cool. All right, so let's get a big old list. It's been a while since we did a proposition that's got 7 parts, but let's do it. So we have established log is continuous, and we've established that it is differentiable. Now, also think about its derivative. Its derivative is never equal to 0. That's never negative. So we know something about how log behaves in terms of increasing. And from increasing, we then know injectivity. And then finally, we'll verify that not only is log nice and continuous and differentiable, it's also invertible. And then maybe we'll talk about what its inverse is, which... spoilers at the bottom of the slides. Okay, and then we'll wrap things up by pointing out a couple of limits of log that are worth just having at the ready. Specifically, as we approach 0 from the right, log goes to negative infinity, and as we approach infinity, log does indeed go up to infinity, although it takes forever to get there. Everything takes forever, but log takes extra forever. Alright, cool. Alright, so basically all of these are going to be pretty quick rattle-offs, which they've kind of already been, because using the integral definition just basically allows us to get away with a bunch of stuff. And here we're going to see, by the integral definition, we know the derivative of log is 1 over x, and that means its derivative is strictly positive, so log is strictly increasing. The end. And if you're strictly increasing, you have to be injective, right? Because if I have x... if I have two inputs lining up, if I have two outputs lining up, it's got to be the inputs are the same, because if they're not, then the strict increasing would force the outputs to be different. Okay. All right, so as we just verified, we know that log of 2 needs to be greater than or equal to 1 minus a half, which means log of 2 is always bigger than a half. And what that means, it's strictly positive. So recall what we're doing here in point 3. We are verifying that for every positive real number, there is a unique real number bigger than 1 strictly, so that log coincides with y. So in other words, when we're bigger than 1, log is going to hit every positive real number, and in between 0 and 1, log's going to hit every negative number. All right, so first we're going to start off by noting log is positive, which means then that I can find a capital N, so that y divided by log of 2 gets strictly less than n. Note that I'm just invoking the Archimedean property here. Okay, so what does this mean for us? Well, multiply both sides by log of 2. That means y is strictly less than n log of 2. Y is strictly bigger than 0 by our hypothesis, which we know is equal to log of 1. And, oh, hey, look at this. We have y living between log of 1 and log of 2 to the n. By the intermediate value theorem, log hits y somewhere in between those two numbers. Beautiful. Pretty good. Okay. And now note, you could make this efficient. You could, of course, find the smallest real number that satisfies this, or something like that, and then plug it in. But, then there's other things you can put here, maybe get some good estimates on what inputs, how to control the outputs of log based on inputs, and things like that. But for our purposes, there is an n. You can try to make it efficient, but who cares? Alright, there we go. Cool, so there we go. We know log now. Every positive real number, log obtains that value, and now for every negative, and also note the uniqueness of such number is guaranteed by 0.2 because we are injective. Alright, so now let's do for the negatives. Well, for any negative number, just negate it over, and then hey, by 3, there is a t that has to hit it. And what do we know about negative log? We know it does 1 over, so let x be 1 over t. Note it has to be in between 0 and 1 because t is bigger than 1. There we go. Y gets hit for this value of x, and again the uniqueness follows from 2. Cool. Alright, now we're just going to combine everything together and verify that log is in fact a surjective function. So take any real number, there are 3 possibilities. If it's positive, then 0.3 gives us an input that hits it. If it's 0, we know log of 1 is 0. And if it's negative, then we know 0.4 tells us that, yeah, there's an input that hits it. So log obtains every real number as a value. And as we'll now verify, log has to be going off to infinity as we approach 0 from the right. And it goes off to infinity as our inputs get infinitely large. So let's see that proof in action. Okay, so I want to prove that we, which one are we doing first? 0, going to the 0 from the right, yeah. Okay, so I want to prove that this holds, which means I want to show that for every m, log of x gets less than negative m for x arbitrarily close to 0. So given an m, I can find a delta, so let's do that. Ooh, going too fast. Okay, so let m be positive. So by 0.3, note there is an m, so that m is equal to log of little m. All right, now take any x that lives between 0 and 1 over m. All right, that means that m is less than 1 over x. All right, now m is equal to log of m. Since log is strictly increasing, we know log of m is strictly less than log of 1 over x. And the log of 1 over x is negative log, so add it over, subtract it over, there we go. Given any m, I can find a delta, so that all x within delta of 0 is strictly less than negative m, so log of x has to be blowing up to negative infinity as x gets arbitrarily close to 0. Cool. And then basically proving that we blow off to infinity as x gets arbitrarily large, so take an m bigger than 0, and then we can find an m in the real number strictly bigger than 1, so that m is equal to log of little m. Okay, so then take any x that's bigger than m, then by the strict increasingness of log, we're done. So given an m, there is a point where for everything bigger than it, our output becomes bigger than m, guaranteeing that we blow off to infinity. So for any arbitrarily large number, I can find inputs that at some point are going to eventually just get strictly bigger. Good stuff. Alright, so there we go. A bunch of properties of log now at our disposal. In particular, this one reveals to us that log is invertible, so let's talk about that. Okay, so log is bijective. It is both injective and surjective onto the reals, so it's got to have an inverse, and naturally we call the inverse the natural exponent. Okay, so in other words, the natural exponent is the unique function from the reals to the strictly positive reals. So note, built into our definition is that e to the x is always strictly positive. Particularly, it's the unique function, so the log of it always spits out whatever you put into the exponential. An exponential of log of y will always spit out whatever the y was. Okay. So note the notation that I'm using right now for the natural exponent. I'm using exp, which is another sort of, once you get far enough in analysis, people just start using exp. But we will, of course, talk about e to the x a little bit later. So we're not going to completely throw that out. All right, let's prove that the natural exponent exponent satisfies some properties that we hopefully remember. Specifically, at 0 it's 1, e to the x plus y is e to the x times e to the y, e to the negative x is 1 over e to the x, and e to the x to the n is e to the nx. So again, like I said, we're using this exp notation. For now, we will get the traditional e to the x in a moment, but let's get working here. All right, so first things first, super easy to show that e to the 0 needs to be 1. Indeed, 0 is equal to log of 1, so exp of log of 1 must be 1. Nice. All right, and now to demonstrate that exponential takes a sum and turns it into a product, we'll note that, hey, if I take log of the product, that's log of the sum, and then log undoes exp, and I get x plus y, and then taking exp of both sides again gives us this. This is one of the reasons why exp as a function is a little bit nicer, because right, when you first encounter having to undo log like this, you're told, oh, exponentiate both sides. Right, but you're very used to applying a function to both sides, so it's kind of weird to think of e to the x as a function sort of initially. And when the expressions get much more complicated, exp is a little more powerful when it comes to that. All right, so similarly, 2.2.3 follows from just noting that logs behave in a certain way, and there you go. And the same deal for 0.4, we already know logs and powers behave nicely, so just use it to our advantage and then take exp both sides in the end. All right, and hey, there we go, some basic properties of the natural exponent quickly established for us. Good stuff. All right, well, now let's prove the big one, the very important one, which is the natural exponential function is the unique differentiable function with the property that it sends 0 to 1 and it's its own derivative. So note, this is a little bit different than what we saw with log, right? What we saw with log is that it's the unique differentiable function, so that log of 0 is 1, log of 1 is 0, all the way around, and that its derivative is 1 over x. Here we see that the natural exponent is the unique differentiable function that sends 0 to 1, and its derivative is not a function explicitly, right? Its derivative is itself, right? So this differential equation is much different. Right? Well, I already spoiled, right? This is a true differential equation. Find me a function whose derivative is itself, right? Differential equations 101, and here we're going to prove what we already knew coming into class, that e to the x is the only thing that does this, but now we actually can explicitly prove it. Okay, so obviously first thing to note, exp sends 0 to 1, and furthermore, 1 over x is the, of course, derivative for log, and note that is strictly positive for all of its inputs, so we know by inverse function theorem that exp must have a derivative, and furthermore, its derivative must look like this, and the derivative of log is 1 over, 1 over, 1 over, gives me that the natural exponent, its derivative is itself. So to look at that nice combo of fundamental theorem of calculus and inverse function theorem working together to verify explicitly, right, a proof you've probably never even seen before, right, that the derivative of e to x is indeed itself. Right, probably the way it was justified to you in calculus was e is chosen, so the slope at 0, 1 is slope 1, and that kind of forces e to the x's derivative to be itself. So that potentially is how you had it explained to you, but of course that requires geometry, which, as we all know, is complete bullshit. All right. Okay, so what have we done so far? We have verified that the natural exponent sends 0 to 1 and is its own derivative. But we're claiming it's the only one that does this, so let's suppose we have a function that does that. Let's prove that f has to equal 2. All right, so define a function h as follows. It's exp of negative x times g of x. All right, well, at first glance, this may not seem like anything particularly too useful, until we remember our hypothesis is not only that g is differentiable and it's in 0 to 1, and it's its own derivative. Missing, you know, like the most important part of the hypothesis here. There we go. All right, let's get that in there. Yeah, why am I missing that? I don't know. What am I smoking there? Anyway, all right. Okay, so naturally, how about we take the derivative of this thing, right? Product rule says we pull out a negative x. Derivative of derivative of the natural exponent is itself. Derivative of g is itself, and and I've got oopsily doodle exp of negative x, and that's gonna go. Oh no, that's gonna go off. That's gonna spill over, isn't it? It's gonna be like right there. Watch. Yeah. No. No. Oh, boo. Oh, boo, boo, boo. Alright, well. Give me a second to turn this equation into a line. Alright, ba-bing. Okay. There we go. Beautiful. So appealing to the product rule, when you take the derivative of this, derivative of the first times the second, plus derivative of the second times the first, derivative of exp is itself, the derivative of g is itself, chain rule note spits out the minus sign, and thus we get 0. So this function h, its derivative is identically 0, which means it has to be a constant, and good thing we know that that the exponential and g of x send 0 to the same thing, because that means that our constant here needs to be 1. Right, so at 0 they send 1 to 1. So we have 1 and we have 1, so 1 times 1 gives me 1. Note if we had different values here, then yeah, not exactly anything at our disposal here. Alright, but anyway, so we've got that, and then now, well, as we know, e to the x, 1 over it is e negative x, so multiply both sides by exp, and we get that g and exp coincide with each other. So now we know the natural exponential function is indeed differentiable, which means it's continuous, and furthermore, it's the only thing whose derivative is itself, again, lining up with all of the calculus intuition we've built up over the years. Good stuff. All right, so what are some other properties of the natural exponent that we are looking now to derive? Okay. Well, one that would be nice, of course, is that we know it's strictly increasing. And as we know, exp built into its definition is that its outputs are always strictly positive real numbers, because again, those are the only things we can actually plug into the natural logarithm. All right, well, exp is its own derivative, so that means exp's got to be strictly increasing because its derivative is strictly positive. Boom. exp to the what the hell? Oh my god, there is all sorts of goofy. Oh my god, I just deleted the whole proposition. Oh no. Oh no. Alright, where is it? There it is. Okay. Alright, so another nice little inequality is that e to the x is always bigger than 1 plus x. Now, again, for big values of x, this is not shocking. E to the 100 is massive. And 101 is big, but it's not that big. So this is really a lot more powerful when it comes to smaller values of these numbers. But it's a very powerful inequality, so worth proving, and it's easy to verify because, as we've already demonstrated, log is always less than x minus 1, so just plug in exp of x, and there you go. We get the classic 1 plus x is less than or equal to e to the x, which is actually a very powerful tool in certain applications. Okay. Alright, so next up, let's verify that just like log, when we look at extremes, so in this case going off to infinity and minus infinity, e to the x behaves quite nicely. So it blows off to infinity as we let x go to infinity, and it goes to 0 as we let x go to negative infinity. Alrighty, so let's say we have, so we need to prove that as we get arbitrarily large, our output gets arbitrarily large, so pick it strictly positive m. And now let's let delta be whatever's bigger, 1 or log of m. Note we need to include the 1 here because this may be negative if m was small enough. But anyway, note that, right, this ensures that delta is strictly positive. And now anything that is bigger than delta strictly, alright, well, delta is bigger than log of m, and e to the x is strictly increasing, so take e to the x of both sides, and there we go, e to the x gets bigger than m, so given an m, there is a point where once you get inputs bigger than it, the outputs get bigger than m. All right, and similarly, to prove that we go to 0, let epsilon be negative. What the oh my god, what is going on? End of the semester, right? I'm just I would be able to say that if this wasn't like the whole semester. Let epsilon be less than 0. That was that was a joke we started making in our analysis class. Somebody like printed a T-shirt with let epsilon be negative. It's a good joke. Nobody laughed. All right. So now let's take epsilon greater than 0. We'll show that the outputs get strictly less than epsilon as we get arbitrarily small inputs. All right. So a similar move as before. So we'll let delta be the minimum of -1 and log of e. And again, the -1 there is to ensure that the delta we're talking about is always strictly negative, right? Because log of e could be positive if e wasn't small enough. All right, but anyway, for any x that's strictly less than delta, then we must be less than log of e. So take e to the x on both sides. E to the x, of course, is positive, so absolute values do nothing, and e and log undo each other, and there we go. The absolute value of that is strictly less than epsilon. So for any arbitrarily small thing, there are gigantically negative numbers, so that once you get past that point, you're going to start spitting out small exponentials. And there we go. Limits for the natural exponential proven. Okay, so we have verified various properties of log and various properties of exp. Right, but of course I've been letting it slip and I've been calling it e to the x. So let's formally make it e to the x now. So in order to do that, let's note a couple of things that must be true now. So for any positive real number, strictly, and any natural number, exp of n log of x, well, we know we can pull the n up here, and then exp of log of x to the n gives me, hey, x to the n. Similarly, if I do exp of negative log of x, well, that's exp of log of 1 over x, which is 1 over x, which is equal to x to the -1. So, hey, that's secretly a -1. So it stands to reason that what we should define to be x to the y for any positive x is exp of x times log of x. And then setting e equal to exp of 1, that gives us the familiar definition of exp, that it is indeed e to the x. All right, so now note here, this justifies why we should do it, because, well, it works for natural numbers, and this also ensures it works for integers. Now, of course, you may go, well, there's other powers to discuss, rational powers. Now, we didn't formally describe what they need to be. We did kind of point out that square root is really, to the 1/2 power or something like that. But let's make that a little bit formal with another proposition. So specifically, we'll prove what are usually referred to as the laws of exponentiation, which are the fact that an exponent to a sum is the product of the exponents. Base to exponent is base to the product, and base times base to exponent is base to exponent times base to exponent. And of course, there's a bunch of other exponential facts you can glean out of this, but these are the three that kind of dictate everything. And in particular, note that if you look at x to the 1 over n and raise that to the n, this guarantees x to the 1, which we know has to be x. And so nth roots you can interpret now as being x to the 1 over n power. Okay, so any sort of reasonable interpretation of powers is completely subsumed by this definition, except for the fact that cube roots allow for negative inputs. So while this definition is very nice, it does kind of forget about those, and that also means you're not going to have access to things like x to the 2/3 for negative inputs. So while this grabs a lot of the cases for exponentiation, it does not get all of them, unfortunately. The only way to truly get all of them is to use complex numbers, but even then it's dicey. There's exceptions in weird cases and blah blah And even still, you're not going to be able to talk about the base equaling 0 and what powers of that need to be. You got to make a decision there. So, oh well. But anyway, let's actually prove that these results are true. And like I said, pretty much any other result about exponentiation can be gleaned from these. So for example, one of them, which I didn't include, is log of a to the x, which just sort of immediately turns into x times log of the base, because, you know, hey, just log both sides. So it's not particularly interesting, but these ones are. So let's prove it. All right, ooh, hello. All right, so yeah, if I look at a to the x plus y, by definition it's that. Then the x plus y distributes, the log of a distributes. Exp of a sum is exp of the product. And hey, a to the x times a to the x, a to the y. Similarly, if I do a to the x to the y, by definition that is exp of y log of a to the x, and as I've already discussed, when you do log of a to the x, you're just going to jailbreak the x, and we can swap the order, and then by definition it gives me a to the x times y. So yeah, like I said, the general power move for log is always true. There it is in action. Good stuff. All right, let's wrap it all up by doing a to the x here. Well, as we know, log of a product is the sum of the logs. Distribute the x. E of a sum is the product of e to the powers. And there we go. Exponentiation rules proven. Beautiful. All right. Well, now that we've got those under our belt, we've got one more thing. Well, there's two more things to talk about, but one more actual content thing to discuss when it comes to exponents and log, and that is, well, now I've got x to any power defined for every positive real number. From calculus, I recall what the derivatives of those should be. And indeed, the derivatives of those are still what you expect them to be. Now, note, you cannot include 0 in here, right? So if you were to try to give, like, this a definition, 0 to the y, where typically what you do there is 0 to the 0, you take to equal 1, and 0 to any other power, you take to equal 0, other than negative powers. So you still couldn't do that because square root, as we know, is not differentiable at 0. So this is truly the most general form of this theorem we could possibly slap together. Right, and likewise, cube root is not viable, it's not differentiable at 0 also, so on and so forth. All right, but let's actually prove this is true, that this is differentiable, and that is indeed its derivative. Well, the good news is that because exp and log are differentiable, that means this function must be differentiable. Again, y is a fixed number, so multiplying by a constant keeps differentiability alive. And furthermore, appealing to the chain rule tells us that the derivative of this should be, the derivative of this is the derivative of itself times the derivative of the inside, which is this. All right, and then we will leave the y alone, and then we will note, oh hey, by the way, 1 over x is e to the negative log of x, pull it in, pull it apart, and there you go. So note, this is a really neat little proof of this fact, the power rule from calculus, that right when you take the derivative of x to the whatever comes to the front, and you take off 1. Right, now we can kind of explicitly see why it goes that way by the chain rule. Right, the y comes out from the chain rule, and the 1 over x sneaks into the exp and picks up the minus 1. So, pretty cool. And you probably saw similar proofs of this in calculus, where you took log of both sides, so you did logarithmic differentiation to get it to work out the way you wanted it to. But, all right, anyway, cool. So there we go. We now have log and exponents at our disposal, and they do what we expect them to do. Beautiful. So one thing you might be asking, of course, is, all right, well, I've got exponents of any bases. What about log of any bases? And you'll see that in homework. All right, and now something else that you may be asking. All right, well, I've got my polynomials. I've got now my ex's and my logs. What are my other favorite functions from calculus? The trigonometric functions. We haven't created them, right? And it's quite shocking that it's pretty challenging to actually create sine and cosine from just the least bound property of the real line. So there's multiple ways of getting at it. One way to get it is, of course, by integration. And it's a pretty lengthy process. I was initially going to do it, but I kind of got halfway through and I was like, oh god, it's already like 30 slides. And so I was like, yeah, okay, I'm not going to do this. But if you're interested in actually creating the trigonometric functions from scratch, you can create them using integration, and what you do is you start with arc cosine, and you don't start with the thing you would think to start with, right? Because hopefully you remember, arc cosine's derivative is negative 1 over the square root of 1 minus x squared. So you might think to start with that as your thing, but that integral, which of course you would have to run from negative 1 to 1, has problems at negative 1 and 1 because the function becomes undefined. So you'd have to prove, first of all, it could be integrated, and you need improper integration to speak of that. So it turns out that's not the right way to approach creating arc cosine. It turns out you want to create it using this, which at first glance might just seem, what the hell is this? Why would you ever choose this? And the way to see why this is right is to factor the 2 out. Because if you factor the 2 out, then you have this divided by 2. And note, if this is a base and that's a height, dividing by 2, that's the area of a triangle. So specifically, this is the area of the triangle inside of the unit circle with a base of x. Note the height would be that. And then over here, you would have this integral, which is the area under the curve of the top half of the unit circle, going from x to 1. So this whole thing here actually gives you twice the area of a sector of a circle, which would give you the angle, which is exactly what our cosine is spitting out. So geometrically, this works. All right. And then, like I said, it takes a little bit of work, but not a lot, but enough to be tedious. This is continuous by its construction. It's also differentiable from negative 1 to 1. Note that this is not differentiable at negative 1 or 1 because this is the square root of 0. It's strictly decreasing. Now, its derivative is negative 1 over the square root of 1 minus t squared. So it's negative on this interval, but no, it's defined on the closed interval. So you have to verify that the strict decreasing extends to the two endpoints. You can prove the two endpoints have to be the minimum and the maximum. That's a way of getting it, but it requires more work than you really think it should. And then you can verify that its range has to be 0 to pi, which is the minimum and the maximum. The maximum occurs at negative 1, and the minimum occurs at 0. And pi, you then straight up just define. This is like how, right, no, we haven't defined pi, so you just go pi is equal to this. Which at first you might just be like, all right, well, that's not exactly the best definition for pi, maybe. But yeah, but when you define it like this, then it's easy to verify that pi over 2 ends up being when this thing is a of 0 is equal to pi over 2. So that gives you an if and only if that cosine is equal to 0 at pi over 2. And right, it guarantees sort of the other properties from there. Right, and so equivalent of that, you then have an inverse function, and note it's only defined from 0 to pi, so you get part of the cosine function. Then you can verify, you can extend it to all of the reals, keep it continuous, keep it differentiable, and keep it and force it to be 2 pi periodic, and then have its increasing and decreasing happen the way you want, and have its zeros be what you want them to be. The translates of pi over 2 and 3 pi over 2. Takes a lot of work to do this, surprisingly. But once you get it, then you get cosine, and then you can define sine to be the negative of the derivative. Then you verify sine's got all the properties you think it should have. You then need to prove that sine's derivative is cosine, which doesn't take a lot of work, but requires some. And then you can create tangent by doing the ratio of the two. And then you're just kind of off to the races. One property that's worth pointing out how you prove it is the formulas for sine of x plus y. So one of the properties that you prove is that sine and cosine are the unique solutions to the differential equation x double prime is equal to negative x. or no, x double prime is equal x. Oh, wait, no, negative x, yeah, right. Brain farting there. So you prove that there are the unique things that are solutions to that. That very similar to the proof of e to the x that we did, where you suppose you've got a solution, you saw that sine and cosine need to show up by a multiplication trick. But yeah, there you go. Alright, like I said, I was planning on doing that, but it kind of sprawled out of control, and so I didn't decide to. So if you're interested, sit down and work out the details. You can actually find most of the details, or at least the big points, in a book called Calculus by a guy named Michael Spivak, who's written a bunch of interesting math textbooks, so check that out. And with that, we got one more video after this, so let's make it.